How's it going, guys? Let's talk about universal gravitation. All right, the attraction of one body or one object to another universally. It doesn't matter if it's a celestial body, which we call planets, stars, all that stuff, celestial body or not. For instance, I am universally gravitationally attracted to this lacrosse ball, and this lacrosse ball is also universally gravitationally attracted to me. Let's talk about how that came to be. Mr. Isaac Newton, you all know him as my favorite person, the father of physics, Mr. Creator of calculus, and so much more. The story of him discovering gravity, I like to put that in quotes, is that an apple hits his head, and he's like, voila, things fall to earth, that is gravity, done. Not quite how it went. In 1665, he was forced to leave his studying at Cambridge due to a bubonic plague outbreak. Sound familiar? We all went through the same thing last year, so maybe we should have discovered something interesting in there. He returned home to an apple orchard and watched an apple fall. He didn't hit his head, but he watched it fall a distance. This is a common misconception, but it makes the story a little bit more interesting if it hits his head. But really, he watched it from afar. And he watched it fall off the tree, and he was like, the apple falls down. And then he looked up into the sky, and he was like, the moon is there. I know the moon is orbiting the earth. Why does the moon just fly away from the earth? What's stopping it? And then he knew the circumference of the earth, and he knew that the moon was about 60 times further away from the earth than the apple was. All right? Don't ask me why or how this guy knows all this, but we're talking about Isaac Newton here. A very smart guy. So, let me pause this real quick.
Good morning, Topsail. Hi, this is Mr. Paul with your morning.
All right, so those are the announcements. So anyways, he was wondering, why doesn't the moon continue off into a straight path? All right, we know the Earth's here. We'll say the moon's, this is not to scale, all right? The moon's there. Why does the moon not go like that, but instead go like this? Why does the moon fall? He was like, you know what? An object feels a force. And he called it the force of gravity. And he said that force of gravity, this is a capital G, not a lowercase g, a capital G, is proportional to the masses of the two objects, so the mass of the Earth and the mass of the moon in this scenario, divided by the distance from the object squared. That's what he realized. All right? But he didn't complete the equation. Like, he didn't make it a complete equation. He said it's a proportionality. These two men coming up made it a complete equation and made it inequality. Finding G. G is what we represent as the universal gravitational constant. And these two men helped discover it. Mr. Henry Cavendish was looking for the weight of the Earth. He was like, I want to find the weight of the Earth. But what he actually found was the density. He found the density of the Earth, and then, knowing the Earth's circumference, he found the weight. Many say that he did actually measure the universal gravitational constant, and you'll see why. Let's watch this video real quick.
On each end of the bar, we put a lead ball. The two balls balance and the bar is free to turn. Now we put another ball on the left side of each of the two original ones. If everything attracts everything else, the balls should attract each other and the bar should move.
I should mention that this is sped up very, very
There
fast.
is an attraction of gravity between the lead balls. First, we weigh a small...
Like that video that you just watched is very sped up. So he used this, he basically, since this experiment is hanging by a string, it's very, very sensitive to like air currents or anything like that. So he had a shed in his backyard, he sealed it off, he put that experiment inside of a wooden box inside the shed. He drilled 2 very small, like centimeter-sized holes, right? And he sat up in his house with a telescope and he watched that experiment happen. He watched it as they attracted each other and he measured it. And he used that to find the density of the Earth. But to find the density of the Earth, he unintentionally also found the universal gravitational constant, but he did not actually write it in his paper. Philip von Jolly actually set out an experiment to experimentally test the universal gravitational constant, which is what we're about to see right here. This is what Philip Jolly's experiment might have looked like, but this is in modern day.
A lead pyramid to measure the force of attraction between it and the Earth. Its weight is 152.166 grams. Now we move the heavy lead ball under the scale, adding its mass to the mass of the Earth. The weight has increased by 1,000th of a gram, which represents the attraction between the pyramid and the ball. When the mass under the pyramid got bigger, the force of attraction did too.
So Philip Jolly, he did that with basically a balance scale, right? You put one thing on here, one thing on there, and it balances out. He put a glass of mercury on one side and a small lead ball on the other, and he placed a huge object underneath it, like a 350-pound stone underneath of it, and it pulled that little tiny metal object down just a little bit more so that the spring was the balance was no longer balanced exactly. And he measured G using that. So what is this constant? Well, we know this from Newton, right? And this is what Cavendish and Jolly used. They're like, okay, m1, m2 over d squared, but there's some proportionality here. There's something missing that makes this, that will make this inequality. And that something is g, which is why we write f of capital G is equal to g m1 m2 over d squared. This is your equation for the force of gravity on universal force of gravity. This g is equal to 6.67 times 10 to the negative 11. Now, if you know this, if you know scientific notation, you know that you need to move this 11 places over. That's a lot of zeros. This is a very, 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 very weak force. All right? In fact, it's, I think, the weakest force out there. Or it is the weakest force out there. It's much weaker than the electromagnetic force, like magnetic force, because we can see magnetic forces happening. Right? So, this practice sheet is on your in the Google Classroom. So go ahead and fill this out. Do some work on this. See how you do. You guys should be able to do it. The only thing missing from this sheet is the mass of the sun, which I have right here. So pause the video and try this worksheet. Next, go ahead, now that you're done with that, go ahead and get on your Google Classroom, click on the link titled NSTMF Gravity, click Create Your Own Universe, and have fun playing around with it. There's a couple of short answer reply questions about the simulator within the classroom link. So try that out and do that. If you have any questions, leave a comment. I'll be reading them, I'll be watching them.